Today we're going to be discussing position velocity and acceleration versus time graphs. So before we look at position versus time graph, we need to understand the difference between distance and displacement. So to understand this, we're going to give an example. A person starts at point A and they travel to point B, and then they travel from point B right back to point A, and they end up in the same spot, point A. So the total distance traveled would be how much the person traveled from point A to point B and back from point B to point A. And the distance between point A and B is 10 meters. So since they traveled the distance once and then once again, it would be 10 meters plus 10 meters, and you get 20 meters of total distance traveled. However, displacement is how much the object or person has shifted from its original position. So the person started at point A and ended up back at point A, so that means the total displacement of the person was 0 meters. However, if the person only traveled to from point A to point B, that means the total displacement would be 10 meters. And so would the total distance, because in this case, the object only moved in one direction and moved to a certain point. Okay, now we're going to be looking at position versus time graph. So first we're going to be looking at a flat line on the position versus time graph. So let's say there is a flat line at about 5 meters. That means the object over a 5-second span is at the same position. So that means the object has not traveled any distance and has also not been displaced at all. So to go from a position versus time graph and make a velocity versus time graph, you would need to calculate the slope of the position versus time graph. And for the velocity versus time graph, if you have that, you would have to calculate the slope of that to get the acceleration versus time graph. So, what is the slope of a flat line? The slope of the flat line would be 0 because there's no change in y. And the y would be the x variable in this case. And the y in this would be the v variable, and this would be a. So, since there's no change and the velocity is 0, since the slope is 0, that means the velocity of a time graph would be a flat line at 0. And since we have to calculate the slope of the velocity graph to get the acceleration graph, then we can also see how acceleration would be a flat line at 0 as well. Okay, so now let's say the line isn't flat anymore for the position versus time graph, but it's still a line. So let's say the line starts at 0 and it has a flat, constant slope line that goes from 0 meters to 5 meter position over 5-second span. So this would mean the distance traveled would be 5 meters. And the displacement would also be 5 meters because the object started at 0 meters and ended up 5 meters away. So to calculate the velocity of this, we take the slope of the graph. So the starting point would be 0, 0, and the ending point would be 5, 5. That would mean we would do the slope formula, which is y2, 5, minus y1, 0, over x2, 5, minus x1, which is 0. So if we do the math, we get 1 meter per second. So now, since the line, it's a line, that means the slope does not change throughout the graph. That means this graph would be a flat line. And where would be a flat line at? 1 meter per second, because that's the slope we calculated. So now we get a flat line right here. And to calculate the acceleration graph, we'd find the slope of this line. Now, the slope of this line would be 0 as well, because it's a flat line. So, which means the object isn't accelerating. And since the definition of acceleration is how much the velocity changes in the object over time, and the object didn't change velocity over time, that means the acceleration would be 0. Okay, so the last example would be not a line, but a curve. So, let's say the object started at 0, position 0, and slowly curved upward until it hit 5 seconds. And so by looking at this graph, we can tell at the beginning of the graph, the object has an almost flat slope, but towards the end, it has almost a vertical slope. So what does this mean? That means originally the velocity was close to or was 0, and at the end, the velocity was very positive. So, and looking at this, we can tell the slope constantly changes throughout the graph. So, since we can't determine a slope at constant slope, we would plot the points of the slope at each time. So, since the slope at 0 seconds was about 0 meters per second, we'd plot it right there, and we'd find a line that would look something like this. Now, you'll notice that this is a straight line. So, now, to go from velocity to acceleration, we'd calculate the slope of this line. So we can do this by using the slope formula, and we'd get a positive acceleration. However, since the velocity versus time graph is a line, that means the acceleration versus time graph would be a flat line because the object is constantly accelerating. Okay, so can you figure out the distance in the given the position versus time graph? I'll give you 3 seconds. So if you said the distance traveled was 5 meters, you'd be right. And the displacement would also be 5 meters. Now, if we weren't given the position versus time graph, but we were given the velocity versus time graph, so let's say the velocity versus time graph was something like this, and you needed to find the displacement of the object, how would you do this? You would do this by calculating the area under the curve. So everything in red right here, you'd have to calculate. So let's say the object was at 5 meters per second at 1 second, and at 0 at 2 seconds, and 0 at 0 seconds. So we can use the area of a triangle formula, or if you're in calculus, you take the integral of the graph. And so since we're going to keep it simple, we're going to do the area of a triangle formula, which would be half base, which would be 2 seconds, times height, which is 5 seconds. So we get the area to be 5 meters traveled. So if we were to graph the velocity versus time graph and the position versus time graph, we can see that the object constantly accelerates in the positive direction, and then constantly negatively accelerates to 0. So to show this, we would show a flatter line getting steeper until 1 second, and then it'll become flat again, sort of like an S. So we can see that at 1 second, the velocity of the object is at its peak, which is like 5 meters per second, which would be right here, since the slope of that part is the steepest, and then it's still positive. The velocity is still positive, but it gets closer to zero, so it would flatten out, and just like the beginning did.